Hello, I'm Cameron Morland. I'm a lecturer in the School of Computer Science at the University of Waterloo. I've mostly been teaching introductory computer science courses, first-year courses that you might take if you come here. And today I want to show you a few kinds of fractals, which are these interesting, they're geometric figures that basically contain a copy or possibly a slightly distorted copy of themselves inside themselves. So I'm going to show you a few examples of this, and then we're going to take a look, develop some code to draw them, and I hope you'll have a chance to try this out yourself in either some language you know, or I'll show you something that does this kind of geometry quite nicely. So let's take a look at some fractals. So for example, this thing is a Sierpinski triangle. And so if you look at it, you see the whole thing is a big triangle, and inside it, it has three smaller copies in the three corners of the triangle that are themselves also Sierpinski triangles that are smaller. And those smaller ones contain still smaller ones and so on. And that makes this interesting structure. We also have this one, which is called a Sierpinski carpet. And again, we see the same sort of idea. In the middle, it's got a big black square. And then around it, it has 8 copies of the fractal, which themselves have each one black square and 8 copies themselves and so on. And again, we get this interesting pattern out of actually a pretty simple idea, if you think about it. Here's another fractal. This is a tree. And again, you may have seen this kind of fractal somewhere. Each branch is in fact a tree, and it branches into 2, and then each branch branches into 2, and then each branch branches into 2, and so on. So all of these so far have been a sort of simple geometric structure. Each thing is plainly contained exact copies of itself that are merely shrunk and rotated or whatever, depending. We also sometimes see, this is another fractal you may have seen, called a Mandelbrot set. And this kind of fractal is developed using a quite different kind of mathematics based on complex numbers. So we're going to first look at the geometric fractals, and then we're going to take a look at, there's a whole array of fractals similar to the Mandelbrot set that are developed using complex numbers by iterating surprisingly simple functions. And so that's what we're going to look at after we've done the stuff with the geometric fractals. Okay, so first we're going to take a look at some of these geometric fractals, and I'll see you in a moment. Okay, so I want to start by making this fractal, the Sierpinski triangle. So we're going to you can use whatever language you want. If you've got some language you've worked on in the past, you're welcome to do that. If not, I'm going to use Snap, which if you've seen Scratch, it's quite similar, but it's more sophisticated. It has a lot of features which are very nice for doing more complicated things. But we're not going to be using them. We're only going to be using the most basic things. If you want to do this in Scratch, that would be perfectly fine. I would suggest using Snap, as I'm going to be doing. So I'm going to show you what I'm doing here. I've set up a few commands already here, and I'm going to use these to, well, basically to set up the screen, and then I'm going to make a program. I'm going to make a new function to draw my fractal. So basically we've got, if you've never used anything like this before at all, we've got a library, and each one of these we've got various commands that we can use to do things, and we're hardly going to touch any of these. So if you've never seen this thing before, I would suggest just pause from time to time. I would open up a browser window and go here and make your own copy of this. So this is at snap.berkeley.edu/snap/snap.html. This is where I'm going to be making my fractals. So I want to make a new command to draw this Sierpinski triangle that we looked at a moment ago. So I'm going to go down to the bottom of pen where it says make a block, and I'm going to say, draw Sierpinski or something like that, whatever. And the difference between these is not important at this point. We're going to use command blocks. Okay, so I want to make this triangle, but I want to be able to control how big it is. So I'm gonna give this thing a parameter. I'm gonna call it size. Okay, so now I've got, it doesn't do anything yet, but I'm creating code to make a Sierpinski triangle of size, and I've got this block here. What I'm going to do is I'm going to put this in here, and I'm going to say let's draw one of size 200. This means that when I call this orange block that's called size is going to have a size of 200. Now, if I go back to my picture, I've got a triangle. So I want to draw a triangle. Well, the first thing I'm going to do is I'm going to write code to just draw a plain triangle. And once we've got that, then we'll think about how to make it look all fancy and fractally. So to draw a triangle, I think what I'm going to do is I'm going to repeat 3 times something, and all I'm going to do is move forward by the size of the triangle, and then I'm going to turn left, let's say, and it turns out I'll need to turn 120 degrees. So I'm going to run this thing by clicking on the green flag, and I got myself my triangle. Okay, so that's all well and good. I've now got the first step to drawing this thing. I've got my one triangle. But now what I want to do is I want to basically make a smaller triangle. So in the bottom corner here, I've got another triangle, and its size is, well, half. So the side length of it is a half as big. So what I'm just going to call the same function again, the one that I'm writing right now, draw Sierpinski. I'm going to call it in my code to make another copy. So I've already drawn a triangle. This part draws a triangle, and then all I'm going to do is I'm going to say, well, after you've drawn the triangle, let's draw another triangle that's half as big. So I'm going to use the multiplication operator to say, take size, multiply it by a half, and then we run that, something happens. But it gets stuck. Because look, I'm going to click the red button to stop it. I said to draw a thing of size 200, which said to draw a thing of 100, size 100, then size 50, 25, 12, and 6, and so on. And eventually I just keep going and going and going. But it never stops. It always makes one that's half as big as it was before. So what we're going to need to do is we're going to say, well, look, if I try to make a triangle that's smaller than like a pixel or something, it's not going to make any difference anyway. So I'm only going to do this if my size is big enough. So if size is bigger than something, I'm going to say, let's draw this thing. So if size is bigger than, say, 5, we can always change it later, then I'll do this. And now when I run it, it stops eventually. So now I've put one in the corner, but I realize I want one over here too. So you know, what I'm going to do, I'm going to take this if, and before I do this move to draw this line of the triangle, I'm going to draw a triangle here. And then before I do this move to draw this part, I'm going to draw a triangle here. And before I do this move to draw here, I'm going to make another one there. So I'm just going to take this and pop it inside here. And I think that's all I need to do. Let's try it. So you can see each time it's now just doing that first line. It's trying to draw the first line, but to draw the first line, it first needs to make recursive copies. It's doing this. It's saying, well, look, I want to draw a line of size 200, but first I'm supposed to do this because 200 is bigger than 5. I want to draw a Sierpinski triangle that's half as big. And so it did that. And notice when it drew this sort of almost big one, it first drew a smaller one in its corner and a smaller one in its corner and so on. So in here it drew this one, and then it drew this one, and then finally it'll draw this one, and then it'll move on and do the top part of the fractal, and then we'll be done. And you can see, yeah, it's now drawing that. It'll move on in a moment and finish off the whole thing, and then we'll have ourselves a nice Sierpinski triangle. There we go. So that's kind of a pretty thing, and you can see the amount of code it takes is pretty minuscule. Hardly any code. So if you've, I would encourage you want to be able to write some code and get stuff working. So take this code, I've got a picture of it here. You can pause the video, go get your own copy of Snap running, or if you have another language that can do this kind of work, try it there and see if you can draw a Sierpinski triangle there to get started doing these fractal things. All right, so this is what we're going for. We just saw some code for it. See what you can do with that, and then we'll take a look at some other fractals. Now I'm going to draw a Sierpinski carpet, which again is, as a recursive structure, it basically consists of a square and then smaller copies of itself. So to do that, I'm going to go back into here and again make a new command, draw carpet, let's say, and we're going to do the same thing I did before. I'm going to give it a parameter for size, and I'm going to call it with size 200, just as an example. And of course it doesn't do anything yet. So I'm going to go back and look. I want to draw a square. So to draw a square, I'm just going to go the length, side length, turn left, and repeat that 4 times, and I should get myself a square. Okay, so I'm going to move to draw a carpet. Well, first of all, I guess since I'm going to be making a fractal and calling myself with smaller values, I'm going to do the same thing that I did before. I'm only going to do something if my size is big enough. If it's too small, I'm just going to do nothing. So if the size is bigger than 5, let's say, then I'm going to do something. I'm going to draw a square, which means I'm going to repeat 4 times. I am going to go forward by size and then turn left by 90. Okay. So if I run that, it should just draw a square. Okay, but if I look back at my fractal, I don't want to just draw a square. On this side, I want to draw a smaller copy and another smaller copy. And so I'm going to basically imagine that instead of just drawing this line across here, I'm going to draw these 2 smaller fractals on my way to drawing the whole line. So I'm going to, instead of having this be a single move size, I'm going to make it into move size over 3, or 1/3 of size. And then I'm going to, well, like maybe I'll just duplicate all 3 copies. So if I do this, it shouldn't change anything. It just draws that. But now, before I draw this first one, I want to here put a recursive call. I want to put in a smaller copy of my fractal. And so what am I going to do? I'm going to say, okay, let's draw a carpet. Before I draw that first third, I'm going to draw a carpet also of size 1/3, like this. And then I'm going to run that and see what happens. So it's done something. In fact, this thing is itself a fractal. It's not quite the fractal we were going for. We'll have to do a bit of debugging. But you can see, look, in each corner, it's got a smaller copy of itself. And let's try making this this threshold smaller. And then this will take a long time to draw. I'm going to hold down Shift and click on the flag so it goes faster. So now you can see it goes smaller and smaller and smaller, and it makes these tiny little things. Now, so what did I do? I'm repeating 4 times. I'm trying to get from here to here and draw the things on the way. So I drew a smaller carpet once, and then I moved a third, and then I moved a third, and then I moved a third. And then I turned and drew this one, and moved a third and a third and a third, and so on. And that's how I got all 4 of these corners. But after I draw this first one and move forward, I need to draw one more fractal here. So all I need to do to fix it is add one more line here. Let's try that. Again, I'm going to turn it on super fast and see that looks like a Sierpinski carpet. So again, this thing, the code, you can see it's very short. It's really only a few lines long, and we get this interesting structure out of almost no code. So I'm gonna leave that up for a moment. You can take a look at that. Once you've and again, you can pause the video. You can go into Scratch if you like, and you can try to make your own copy. And once you've once you've got that going, you can play with it, see what other changes you can make, see if you can make it do other things. All right. All right, so there's one more fractal I'm going to show you, and again, it's this tree fractal. So what I'd like you to do, try to think about how would you write this. So again, it's a thing. I need to draw a line, and then I've got some smaller pieces. What do I need to do in order to make those work? Try to pause for a minute, pause your video for a minute, go off and see if you can write your own. One thing that may be important that you may find necessary to get this to work, if I start here, when I move up, I'm then going to change some angles or whatever, but if I wanted to be able to draw another one afterwards, once I've drawn any given stick, I have to change it back so I end up back at the place I began and facing in the same direction. And if you may find troubles with that if you don't do that part. So try to do that. Pause for a minute right now and go off and make your own. And then I'll show you a solution that I wrote. Okay, so here's a solution. I hope you've got your own running now. What do? Well, I check to see if the size is big enough. And again, you could use whatever threshold you want. Then I move forward, I turn to the right, and I draw a smaller recursive thing. That's this part. And then I turn to the left and draw another one. And again, I wouldn't have to put 90 degrees between these, but I have to choose some angle. I draw another recursive tree. And then this is an important part at the end that may be counterintuitive. I need to turn back so that I'm facing straight up again. And then I need to move back to where I started from. And then that's all it takes. And this thing draws this nice tree, again, out of almost no code. So I hope you find that interesting. I hope you got a version of your own working. That's pretty. It's a nice thing. And that's the only those are the three structural recursive fractals, sort of geometric fractals that I want to show you. So I hope you enjoyed those. So based on what we've seen so far, you might conclude that fractals are always some sort of structure, like the Sierpinski triangle, that contains literally some smaller copies of itself directly as defined in the code, like it is with the Sierpinski carpet and the tree and so on. All those fractals we've seen so far are defined that way. But that's not the only way we can build fractals. There's other kinds that you may have seen, such as the Mandelbrot set, that are defined using a completely different technique based on iteration of functions on complex numbers. So I want to show you a little bit of how to do that, and then I'm going to give you some down below or somewhere on this website. We're going to have a copy of the code that I use to generate these, so that if you want to play with it yourself, you can go do that. So I'm going to go in here, and here I'm going to just talk a little bit about what I mean by iterating a function. So I'm going to define some function, and it'll depend basically which function I use will affect which fractal I create. So I'm going to create some function f of z, and I traditionally we use z to refer to a complex number, and it's something. What it is doesn't matter in general right now. We'll talk about a few specific examples a little bit later. So what I'm going to do is iterate it. So what that means is I'm going to start with some value, which I'll call, let's say, z0, and that's going to be something. Maybe it'll be 0, maybe it'll be something else. And then I'm going to call f of that function. And I'm going to make that new value be a new thing. So z1 is going to be f of z0. And then, so that's a new value of z1. And then I'll do that again. z2 will be f of z1. And so on. z3 can be f of z2. And I can carry on as much as I need. And depending on what my function is and what I'm doing with it, I can get fractals out of this kind of thing. So in particular, if I use the function f of z equals z squared plus c, and I use, basically I use c to represent a point on the complex plane, and I use z to be, z0 is 0. If I iterate that function in this way, I will get the Mandelbrot set. So that's what I did. I've got some code here, and when I run it, basically it's going to take a look at each pixel on the entire screen here, and it's going to do this calculation. It's going to iterate this, and basically if the value of this, if these numbers get really big, if like Z50 is really huge, then it'll draw a point that's white there. But if it continues to be a small number that's close to 0, it'll draw it in black. And so if we get that, and we draw these things in random order, we get this. So probably that is an image that you've seen before, the Mandelbrot set. And it really comes out of this simple function, f of z equals z squared plus c. Again, so this is the complex plane. Horizontally, we have the real numbers where the center of the thing is, and then vertically we have the imaginary axis, and these define the complex plane, and that's how this thing is defined. So that's again, the details of the math I don't really want to get into right now, but it comes out of this simple equation. Another kind of equation that we can get, another kind of fractal that we can get are called Newton fractals, and they come out of a different sort of equation. So this one here, the one we saw here, f of z is z squared plus c, that'll give us the Mandelbrot set, as we saw before. Well, now I'm going to make another one. I'm going to choose some function g, and then my f of z is going to be z minus g of z divided by g prime of z. And this equation here comes out of Newton's method, which is why these are called Newton fractals. So if I do something with this with some function g, and I again iterate these things, what Newton's method does is it'll find the roots. It'll find the values of z for which g of z is 0. So for example, let's choose g of z is z plus 2 times z squared plus 1. And I think you can see if z is negative 2, of course, this piece here will be 0. So z equals 2 is a root of this thing. If you know about complex numbers, you'll know that I is that number which when you square it, you get negative 1. So it's not a real number, of course. But if I put in I for z, I squared will be negative 1, and so this piece would become 0. So I is also a root of this function here, and so is negative I. And so there are 3 roots to this, negative 2i and negative 2. Negative 2i and negative I. And every point on the complex plane will go to one of these roots eventually. So if I run this function, what I've done is I've basically taken each point and iterated it using a function of this form, and depending on which root it goes to, I color it one color or another color. So let's see what that looks like. So again, that's a very simple, this just comes out of this equation, g of z is z plus 2 times z squared plus 1, put through this Newton function here, and that gives us, if you're over here on the left, that's the root z equals 2, and then where it's green, in the middle of where it's green, and up here in the above the middle where it's blue, that's the root I. And down at the bottom, it's the root negative I. So any point on this plane that's orange, if you start there on the complex plane and you iterate it through this process, you will get to that point I. So these things, again, I'm not going to go into all the details of the math behind them. It's a little bit much for the amount of time that we have. But I hope you see that these things are fractals, and they come out of completely different math than the recursive ones that we were looking at a few minutes ago. So I hope you enjoy that. If you want to talk more about this in the Q&A session, bring it up and say, I want to hear more. Let's talk about that. So I hope this is interesting. And so now we've seen the two kinds of fractals, two common types of fractals. We've seen the regular recursive types, like the Sierpinski triangle, and we've seen these iterative ones, like the Mandelbrot set, and these Newton fractals. And I hope you find those beautiful and interesting, and I hope you enjoyed this. All right, bye for now.